So hi, today we will continue with chapter 3, part 3. We will talk about linear density. So what's linear density? We have a direction, this blue one over here, and on that direction you can see some atoms. This direction goes through some atoms, and we can calculate how full that direction is. In order to do that, you have to calculate number of atoms on that direction and divide it by length of that direction. So here we are given FCC crystal structure 110 direction. First, draw FCC crystal structure. Afterwards, choose axis system. For this one, my axis system will be like this. If I draw this direction, I get this blue one over here. Now, how many atoms this direction goes through? I have one radius over here. Let's take it out. One radius, two radius, and one radius over here. So in total, 4 radius divided by 2, you get 2. That means number of atoms this direction goes through is 2. So what's the length of this direction? If this side is A, this one is also A, I'll have this kind of a triangle. This is 90 degrees. It will be A under square root of 2. So I can write it now. Linear density for 110 direction will be 2 divided by A under square root of 2. And if you remember from previous lecture, we created relationship between side A and radius for FCC crystal structure, and it was 4 radius equals to this. You can replace A with radius over here, and plus you can replace R from periodic table. So for example, you have an iron. For iron, the radius we can get from periodic table and replace it. Next, planar density of 100 plane in iron. Planar density equals to number of atoms divided by area of plane. It shows how full one plane is with atoms. So first, you have to draw BCC crystal structure. As you can see here, I have 2 pictures of BCC crystal structure. Next, draw 100 plane. Open the bracket, take reciprocal. It will be 1 infinity infinity. Choose axis system. Let's take y and x. This plane should intersect x-axis at 1 and be parallel to y and z. It will be this front face of the unit cell. And I will do the same thing over here on the left picture. So the size of the cube is A, and it is a rectangle. So area of the plane will be A multiplied by A. For number of atoms, this plane covers 1/4 part of each atom, and I will have these atoms. This plane does not have this one at the center. It is right at the center. We are just taking the surface. That's why I will have only these 4 corners. So I will have 1/4 multiplied by 4. It will be 1/8 a squared. And why did I not take this one at the center? Imagine it this way. I am drawing from this side. Let's say it is an eye. That is center atom. And this one, my plane. This atom at the center is not on that plane over here. Now for this one, 1, 1, 0 plane, I will choose the same axis system. Open the bracket, take reciprocal, 1, 1, infinity. This plane should intersect x-axis at 1, y-axis at 1. Connect these 2 points. This plane should be parallel to z-axis. That means I will extend this xy line parallel to z. So it will be this plane. I will do the same over here. This 1, 1, 0 plane. As you can see, this plane covers 1/4 part of these corner atoms, and this one at the middle will be crossed by that plane. If I take this picture out, it will look like this: 1/4 part for each corner, and the 1 for the middle one. So 1/4, and this is 1. And the sides will be a. This one will be a under square root of 2. The planar density would be equal to number of atoms, 1/4 multiplied by 4 plus 1 over area of rectangle. This will be a under a square root 2. So that's it. And if required, you can replace this a over here and this one over here. B is R. For BCC crystal structure, we have done it in previous lecture again. 4R would be equal to this, so you can do replacement if required. Here I have a summary of linear density, planar density, and atomic packing factor. In order to solve all three, we have to take some portions of an atom. That's why I am doing this slide. So imagine here I have a direction. This direction goes through the all of this atom. One portion. Imagine you shoot an arrow, and this arrow goes through all of an apple. Let's say it will be one portion. All of this atom's area is inside rectangle. One portion. All of this atom's volume is inside of that cube. One portion. This direction goes through the half of this atom, 1/2. Half of this atom's area is inside this rectangle. This atom is centered at the face diagonals, so half of its volume would be inside cube. It should be something like this. 1/4 part of atom's area will be in that rectangle. Now here, this atom is centered around this line, so its volume will be like this. Inside the cube, I have this kind of volume, 1/4 part. Imagine you split an apple into 4 parts, and one part is inside that cube. So here, this atom is centered at the corner of a cube. It will be 1/8 part. If you try to color it, this part will be inside. We may have another kind of planes. For an example, FCC 111 plane. For FCC crystal structure, imagine we had 8 atoms at the corners. I will draw the atoms which is interesting me. I will not draw all of it to make picture simple. So 111 plane will be this. This one is Z axis, Y and X axis. So 111 plane and atoms. I will have this corner atoms. I will have face atoms, but I will take just 3. 1, 2, 3. So if this side is A and A, side of the triangle will be A under square root of 2. So I have atom over here. So number of atoms. The half of the face atoms would be inside. For these corner ones, all sides are equal in this triangle. That's why each will be 60 degrees. This is 60 degree. Total is 360 degree. So it will be 1/6 part. So what I have, 3 corner atoms. Each one is 1/6 plus 3 face atoms. Each one is 1/2 divided by area of triangle, where sides are equal to A under square root of 2, and etc. For BCC, this plane will change. You can try it for yourself. Now, we have single crystals, polycrystals, and amorphous materials. For single crystal, the atomic arrangement is perfectly periodic and is repeated without distortion. What is this? If you look at this picture over here, if you compare with this one at the right, as you can see the difference, this one is periodic. This one, I have some distortions. One example, here my orientation comes like this, afterwards change to this, and then to this. So change in orientation. In polycrystals, poly means more than one. And in single crystals, I don't have a change. Everything is in perfect condition. What does this mean? This one is a single crystal. If I take some part over here and analyze it, I will see that unit cells has certain orientation. So let's say it's X, Y, and Z. So all unit cells are oriented in this way. If I take another part and analyze it, I will see that I have the same orientation because my pattern was not disturbed. So we call this kind of materials single crystals. And for crystals, as you can see, if I measure from one side, I will have one orientation. If I measure over here, I will have different kind of orientation. So how polycrystals, let's say, happen? Here, this gray one is liquid. This reddish one is solid. Each cube over here, this one over here will be one unit cell. So what has happened? As temperature drops, liquid is transformed into a solid. So as time goes by, the atomic atoms from liquid join to this solid. Liquid atoms over here will join this solid. So this solid starts to grow as liquid decreases. There will be a time the solids will increase so that I don't have liquid present. So as you can see, I can trace borders of these parts of solid. So what you can see over here, you can see this orientation comes as this way, changes and changes again, because these solids grew in different parts. I have different orientations. This red ones which I have drawn here is called grain borders. And under microscope, you will see something like this. These ones are grains, and these black lines are grain borders. That's it, what you see under microscope. As you can see, I have different orientations over here. I have different axis system for each of them. So let's continue. Single with polycrystals. Here I have BCC crystal structure, and two directions are given. This one is 100 direction, and this one 111 direction. You can see atomic arrangement. I have 2 here, 3 over here. If I calculate linear density for both, for this one it will be 1 atom over A. For 111 it will be 2 atoms over A under square root of 0. So linear densities vary. That means this material will have different mechanical properties. As an example, modulus of elasticity for 111 plane is 273 gigapascals. For 100 direction, modulus of elasticity will be 125 gigapascal. That means it will be difficult to transform material in this direction. It will be easier to deform material in this direction. So I have different properties when I measure from different directions. It is called, these materials are called anisotropic materials, and single crystals are anisotropic materials, because whenever you measure, I have the same X, Y, and Z. So I will have the same directions. That means always I will get small value in this direction, higher value in 111 direction, and etc. But for polycrystals, we have more than one crystal, and each time orientations are changing. For an example, for this one over here, my orientation are like this. For this one, I will take orientations like this one. And for the third one, I will take this. So what will happen when I measure, let's say, in X direction? Let's say I am measuring first in this direction, afterwards like this. Let's assume that my material is weak in X direction, medium strength in Y direction, and it is strong in Z direction. When I measure this polycrystal, and when I measure in X direction over here, like this, so what I get? X, Z, and Y. If I take an average, what will happen? I will get some average value. Then let's move on to measure in this direction, Y direction. Now what I get for this material? I have Y, X, and Z. Again, I will have some average value. Third time, I am measuring in this direction. What I have? Z, Y, and X. If you see, when we have polycrystal, we are taking an average value of all grains. As you can see, strength values. I have weak, medium strength, very strong. And the same applies for all of it. Because I have various of random orientations, on average, I will have the same mechanical properties in all directions. And it's called isotropic material. Isotropic means whenever you measure, you get the same answers. And polycrystals are isotropic materials. And the reason I have explained over here, because you take an average. What if polycrystals are textured? What does this mean? Imagine you have this kind of material. It is polycrystal. If I try to reduce its radius, so what will I do? You have some rollers. So this roller over here is pressing, applying force to this material and reducing this diameter, and this roller forces unit cells, grains to align. You are forcing grains to align. So in this part, my material will be textured. And that's why this part of material will be anisotropic, and this side will be isotropic. Here I have included some values of different elements. So modulus of elasticity for aluminum, copper, and iron. It changes with direction. So here we are given 3 directions: 100 direction, 110, and 111 direction. As you can see, these values are changing with direction. But for tungsten, all are the same. Modulus of elasticity is isotropic over here. And that's it for today. Thanks.